Sure, shall I start? Am I audible, sir? Shall I start? Yes, sir. Dear participants, I welcome you all for the second day program of 2 days international webinar on advanced functional materials for biomedical and energy. Today, we have the first speaker, Dr. Xiaoxiao from China, and I request Dr. Baudina to introduce her and chair the session. Over to Dr. Baudina.
Thank you, Judith. So, good morning to everybody. So, our second day, we will have two speakers. Let me introduce our honor and first speaker, Dr. Xiaoxiao Huang. So, she is a professor at School of Material Science and Engineering at Harbin Institute of Technology. So, let me tell you information that Harbin Institute of Technology is among top 10 university in material science and engineering in China and top 50 university in the world again in material science and engineering. So Dr. Xiaoxiao got her PhD in material science and engineering at Harbin Institute of Technology in 2005. Now she is full professor, and her research expertise mainly focus on design and preparation of new ceramic and carbon materials, for instance, like for lithium-ion batteries. She authors and co-authors around 100 papers, and she has more than 20 patents. Her talk today is about research on oxides, anode materials for lithium-ion batteries. So, Xiaoxiao, the floor is for you. So you can start your presentation, please.
Okay, so I will share my content with you. Why? Thank you very much. I want to thank Dr. Judith first, because I cannot use the Google app, so maybe there are many troubles for you to use this Zoom for this international conference. Pardon. Can you say it and hear me?
Yes, we can hear you.
Yes. You know, today is a Chinese holiday. It's a very famous festival in China today. Its name should be Dragon Boat Festival. So happy festival today, everyone. Today I want to share some our group research results with you. The title of the presentation is about the research on oxides anode materials for lithium-ion batteries. I'm Xiaoxiao. I came from Harbin Institute of Technology. What I want to share with you today is about the two parts. The first is the oxide-based anode materials, and the second part should be the anode material research. I want to summarize some results from my group and share it with you today. So firstly, I want to give a very simple introduction about this research field. This picture is about the schematic diagram of lithium-ion battery. We know that for the LIB, it's a very complex system that includes the positive, the negative, and the electrolytes and the separate so on. It's a very complex system. But what we want to focus on today is about inert material. This is a very important cancer of the inert material, the tin oxide. It's so important because the tin oxide has a very high theory capacity. The value of this material can be reached up over 1,400 mAh per grad. Because this material, during this material in the electrochemistry process, it has two steps to offer the capacity. From these equations, we can know that for this material, the mechanism to storage the lithium is about the first is we call it as a conversion type. That means the tin oxide with the lithium ion will transfer into the tin metal, and then the tin will continue with the lithium ion transfer into the lithium tin alloy, because this step will be the alloy type. And this oxide as anode material, we want what's the purpose we want? Is that we want this material can be a higher capacity, a very stable rate performance, and better cycle property. And also we want it has a higher SAE. SAE means the initial Coulombic efficiency. We want this material can be a higher capacity. And also we want it for the new development demands. We want it has a flexible, bendable, or the bender additive free, and we want it cheaper. It's a green technology, and it's a high productivity, and so on. So we want what can we do for this purpose? We can improve this material's conductivity, and we want it can be a small expansion during the electrochemical process, and we want it has a stable SEI. SEI means a stable electrolyte film, and we want the particle aggregation will be controlled, and also the reversibility of the reaction will be carried out. But the most important we want to do is to improve the conductivity and to control the expansion of this material. So for these two purposes, and we try to design the material structure and try to get improved properties. So the first material we want to design is we call it as CGN at tin oxide. Let me interpret the means of this material. We use the raw material with non-woven cotton because this anode material copied the cotton's structure. So this material should be a flexible or the bendable material. We sucked this cotton into a gel solution. Gel means graphene oxide. We sucked it in the gel solution, and we added the tin ion into this material, and then the heat treatment will be used in this material, and we got the anode material is a cotton with a RGO. RGO is a graphene. We can we can think it as a graphene and tin oxide. So we named it as a CGN tin oxide. Let me see the microstructure of this material. After we heat treatment this material at a different temperature, we can see that the crystal or the faces is the same. And from the ICI, we can see that every carbon fiber was covered by the graphene. And the EDP results show that on the surface of the carbon fiber, they are homogeneously anchored plenty of the tin atoms. And when we take the TEM of the graphene, we can see that the small size of the tin oxides anchored on the graphene surface. And the size of the oxides should be tens of nanometers. So we tested the property of this material. We compared the three kinds of the material. That means the carbon tin oxide. The carbon means that we didn't put the graphene on the carbon fiber surface. And the CG tin oxide means that we use another polymer to transfer into the carbon. And the CGN means we use the graphene with the carbon fiber and then with tin oxides. So we compare these three materials, we can see that the CGN tin oxides show a better specific capacity and a very high Coulombic efficient. We can see that the capacity can be reached up about the value of 600. Because we think we improve the conductivity and we use the Cotton's structure to control the bulk expansion. Even we got a good result, but we also think for the tin oxide anode material, how can we get a very how can we get a higher capacity with a stable performance? From the other research results and many references told us that there have some ways to do it, such including the nanomaterial. We make the nanomaterial, or we can select other metal atoms to dope in the tin oxides, or to design the hollow structure, or to make the interface design. But about this ways, we can see that we think that the nanomaterial is a very effective or a very easy way to do it. But for the nanomaterial, let's have some advantages and disadvantages. The advantage is that if we make the tin oxide as a nano size, it will be low the bulk expansion. That means the big expansion will be controlled. And the nanomaterial, usually we know that it has a higher interface. And the so small size maybe can make the make the reaction velocity will be increased. Also, there also exist some new problems. Nanomaterial can be reunion or aggregate when we use it. And because the nanomaterial has a higher interface, so there may be a more ICI produced. When the ICI was being produced, that means more lithium ion will be wasted. That means more ICI and more lithium ion will be wasted. So we don't want the ICI unstable. We want it stable, exist in the process. And the last is that even we make the tin oxide to the nano size, but the conductivity cannot be improved if we don't add some other conductive material. So we want to try to design a novel structure to design the tin oxide for the LIB use. About the based about oxide at OMC material. This is about the. We want to try to solve the conductivity, the bulk expansion, and the higher reaction, and so on. And then we want to get a better electrochemical properties. What's the OMC? OMC means outward mesoporous carbon. I want to interpret this material from these pictures. I want to try you to know how we can design and get this material. Firstly, we use the ferroferric oxide covered with a polymer. It's a kind of acid. It's oleic acid. We can get the ferroferric oxide with about 15 or 20 nanometers. It's very easy to get it, and then we get the we use the solvent evaporation to get this structure. This structure is the orderly arrangement of the ferroferric oxide. Because during this evaporation, the ferroferric oxide will be self-assembly arrangement. So we will, until the end, the material will cover or will copy this structure. When we get this orderly arrangement structure, and then we added the tin ion into this material, and then with a heat treatment process. After heat treatment, we can see that on the ferroferric oxide surface, they are covered a layer of the carbon, and the tin ion will be transferred into the tin oxide, and the tin oxide exists on the surface of both between the two ferroferric oxide. So the size of the tin oxide will be controlled. So after the ferroferric oxide was removed, we can get like this hollow carbon with ultra fine tin oxide. So we want to try to summarize the structure's character feature and let you clearly understand this microstructure. Firstly, it should be OMC. OMC that for the hollow carbon. The hollow carbon's OMC structure copies the ferroferric oxide structure. And second is Mesoporous, because the ferroferric oxide size is about 15 or 20 nanometer. So after heat treatment, the hollow size should be smaller than the ferroferric oxide, and this should be actually we got the hollow size should be 10 to 11 nanometers. So it's a very small size, and this size is very helpful for the lithium ion to move in or out. And third is a 3-dimension carbon network. We can see that the hollow carbon will be connected to each other and to form the 3-dimension or the conductive 3-dimension conductive carbon network. So it will helpful for the improvement of the conductivity. And the fourth is a hollow carbon. Hollow carbon means that it's with a carbon shell, and the inner is a hole. So for this structure, when the tin oxide experiences the bulk expansion, and this hollow carbon structure will give a buffer or control role to help the tin oxide. That means that the tin oxide cannot be broken. You know, the tin oxide will be a very big bulk expansion. The value should be when the anode material experience the charge or discharge process, and the expansion should be get about 358%. So it's very big bulk expansion. But this hollow carbon will help it to control the bulk expansion. And the last one and the most important is that we can use this we can get the ultrafine tin oxide. The ultrafine tin oxide and the OMC structure, which not only shorten the diffusion distance of the lithium ion, and will be decrease the polarization, which both of them can be helpful for the properties. So we designed this material and we got it. Let me see the microstructure of the materials prepare process. These two pictures about the ferroferric oxide with OA. And we can see after the solvent evaporate, and the ferroferrics will be arranged orderly arranged self-assembly. And after the ferroferric oxide removed, and we got the tin oxide at OMC material. From this picture, we can see that the hollow carbon will copy the ferroferric OMC structure. And when we test the lattice spacing, we can get a very small size tin oxide. The size of the tin oxide should about 5 nanometer. It's very, very, very small. And we get this value because we calculate based on the SRD result. This about the tin and oxygen mapping, and we can get the detailed microstructure of this material. TJ result tells us that for the tin oxide at OMC material, we can get a very high content of the tin oxide in this material. From this result, we tested from the RT to the 700 temperature. We can get the tin oxide content is over 19%. For comparison, we also prepared the tin oxide the tin oxide at RMC. RMC means that OMC is the ordered mesoporous carbon. RMC is a random mesoporous carbon. So when the carbon is not exist with the orderly arrangement, and we make the RMC to compare with it. We test the materials property. Then it's about the electrochemical performance. The first picture showed us that this anode material experience a two-step electron reaction, response for the conversion reaction and the alloy reaction. And the second picture, we can see that even at the different current density, we can get this very stable result. And the third and the fourth is a comparison for the tin oxide between the tin oxide OMC and the tin oxide RMC. It can be seen that for both of the cycling testing of the specific capacity, the former is better than the later, and we get a more improved result about the capacity. The value will be 930. Even when we test it at a higher current density, it's about 5 I per gram. The capacity still remain about 500. So it's a very excellent result. Also, we compared our result with the reference result. It shows that this structure is very benefit for the improved performance. ES curve tells us that the conductivity of the diffusion efficient, and we also calculate and test the OMC structure. Its benefit for the lithium ion to transportation. That means it can be uniformly to let the material in the electrolyte and to shorten the transportation distance and to get improved performance. This picture is very interesting because this picture is we test this picture after the tin oxide at OMC material for after 150 cycles. That means when we test the material and then we take the material to test again, what we got, we can see that the structure has been maintained. They are not be broken or not changed greatly during this material, even this material after a long time cycles. So for this material, we think that it has three results. First is that the large specific surface area may be helpful enhancing the specific capacity. And the second is a 3-dimension conductive carbon network ensures the fast electron transfer, contributing to rate capacity. And the void or the hole in the material can be very helpful for the buffer, the large bulk expansion, improve the cycling stability. So this is the first part. And the second part, we want to summarize some result about the iron material research. We also did some other kinds of the iron material, such as carbonate, or the metal oxide, and others. We want to introduce it to you. First is about the magnesium, cobalt, carbonate, and RGO material. You know, when we make the RGO, use the redox method, we also use mining potassium. And when we get the RGO, the potassium will be waste. So we want to use the potassium. It will be in the material with potassium ion, and we can adjust the content of the cobalt ion and gauge the different material. It should be cobalt carbonate or the manganese carbonate, or when we adjust the ratio of the magnesium ion and the cobalt ion, we can get the double metal carbonate. It's very interesting because we can see that some microstructure and better electrochemical performance. This is the first kind of the material. The second is about some oxides. We also we use the hydrothermal reaction and thermal treatment to get kinds of the oxides, such as double metal oxides, or the two kinds of the oxides with different kinds of the carbon, and to make the composite for the iron material application. During this research, above this research, we get the result that the graphene is very important for informing the conducting skeleton. And when we adjust the technology, we can get the oxide particles with kinds of the porous, and we get a better yes, here to get a better performance because we think that this structure with a more active size and can help for shorter diffusion paths and speed up of electronic transmission. And another kinds of the materials preparation with I want to show you is that it's named the gel swell. I don't know why the PPT, the slide will automatically move. We called it as a gel swell. That means that we firstly to prepare the gel precursor and put the precursor into the oven and use a very short time. It's about 1 minute, and we can get kinds of the oxides with carbon. The characteristic of this method is that it can be fulfill the high productivity, and is very cheap ways to get, such as ferroferric oxide, magnesium oxide, or the double metal oxide, and so on. We can adjust this microstructure with a non-layered two-dimension material, and the time for the preparation process is very short. and it's with a high quality. And the microstructure on the chips with plenty of the pores, which is helpful for the lithium ions transportation. So this result has been accepted by this AM journal is in the 2018. At last, I want to. We also have did some research about the nano silicon anode composites, and we also did some in the lithium sulfur battery. We designed the cathode holster for the sulfur, and we also make some research on the aqueous battery cathode material. And now we want to try to start the single atom metal catalytic materials research. So the main conclusion about this presentation is that first we think with electronic vehicles demand, we need to develop new anode material. And anode material with different microstructure and modified by graphene, by nanocarbon, or by other kinds of the carbon material can greatly improve the performance. The third is that metal oxides, and carbonates have high specific capacity and excellent cycling performance. And we think that the development of the new anode material has a long way to go, and the scientific research should be go ahead. The modification of nanocarbon material is one of the effective ways. That's all the what I want to share with you. At the last, I want to use a very short time to introduce my university, Harbin Institute of Technology. We call it as HIT. In China, HIT has 3 campuses located in the Harbin. This is the Heilongjiang in the north of the China, the Heilongjiang province, and the second campus is in the Shandong province, in Weihai, and the third in the south of the China, in Shenzhen, is in the Guangdong province. So this is about the campus of my university, and you know, on the 7th of this month, my university just has its 100th anniversary. So for my university and for me, welcome everybody come here to visit, to study, and to do some collaborative research with you. Welcome. Thank you very much. Thank you. This is the members in my group, and I wish to collaborate with you in the future. Thank you very much. That's all.
So thank you very much, Xiao, for this insightful presentation. So firstly, we would like to thank you for being with us during this event. And also we would like to wish you, how to say, good holidays, and for joining us, even it's a festival, the Dragon Boat Festival. So we congratulate your country and
Dragon Boat Festival, yes.
So let me start. I think I visited your institute, so it's very beautiful city, and it's very beautiful college, you know, and people are very happy.
Hopefully you can come here again.
Yes, I told you, maybe I will visit with Judy. So meanwhile, there are so many questions from the audience. That means because they are interested in your work, but maybe there is some things you didn't explain more because maybe you address your presentation to maybe people that are more experts, but we have participants from different backgrounds. So let me start with some about SNO2. So one of the question is, can tin oxide be used for solar cells application?
The application? The anode materials application? Oh, pardon. The Wi-Fi. My Wi-Fi is not very stable, so I cannot hear clearly. Can you say again?
Yes, I'm repeating. So, the question is about using tin oxide for solar cells.
Yes.
Can we use tin oxide for solar cells?
Solar cells.
Yes.
Pardon? Solar
cells.
Uh-huh.
Is that possible? Can we use it or not? I think I have seen some papers related to tin oxide solar cells.
We use the tin oxide in the anode material in the LIBS. Oh, pardon. What?
Okay, let me ask about another question. How we can identify the OMC?
OMC.
Yeah, how we can identify? Only by TEM or which techniques?
You mean you want to get the OMC?
How we identify? By X-ray diffraction, by TEM, by SEM? Which technique to
SEM is not good for the OMC structure.
Okay, so
we should be. We use many ways such as TEM or the HRTM or others. Yes. Wait,
okay, let me check other questions because we are receiving so many questions at the same time. So I'm just choosing some questions.
Thanks for your interest. Yes.
So the next question is about can tin oxide be prepared by co-precipitation method? Can you hear me? Xiaoxiao, can you hear me?
Yes, I hear. What's the problem?
They are asking about the preparation of tin oxide by chemical routes. They ask you if we can use co-precipitation method to prepare tin oxide.
Yes.
So it's possible to use the co-precipitation.
Sorry, because I cannot continue to hear clearly about your question. I don't know whether you can hear me.
Okay, just a minute. Can I post the question?
Can you hear me?
I will copy and paste the question to you on the message, okay?
Sorry.
Can I copy and paste the message to your account?
Can you hear me? Hi. Oh my God, I cannot.
Just a minute. I try to find some way to send you the questions through to Zoom. Okay, just a minute, please. So okay, I'm just.
Sorry.
Just a minute.
Can you hear me? Yes.
I'm trying to.
Yes, I can hear you.
I'm trying to write the message for you.
Dr. Bawadina, sorry for the interruption. Shall I ask the questions to her?
I don't know whether.
I'm trying to send. You can ask, of course, because I'm trying to send her the message, the questions through Zoom.
Chat box.
Oh my God.
Maybe she is not. maybe I got disconnected, or I don't understand.
Dr. Xiaoxiao?
Hello. Hi.
Can you hear me now? Xiaoxiao, can you hear me?
Yeah, I hear you. Now I can hear you, but not almost I can hear you. Sorry.
Okay, can I send you the message? Can you check your message on Zoom?
Check the no Zoom. Check what?
I typed the question on Zoom chat box.
Oh, yes.
So you can read the questions. It's much easier for you.
How to check it? Here. Oh, yes, I got it. So many questions.
Yes, you can start. You can choose a few of them. You cannot answer all of them because so many. So choose some of them and you can answer, please. It's much easier like this.
One by one.
Yeah, you can choose. Okay.
Choose. Okay. No. The last is there any method to increase the performance of the batteries by other than carbon nanoparticles?
Exactly.
Can you hear me? Yes.
So we
tried other methods to increase the performance, but to improve the conductivity is very important for the improved performance. So the graphene is the best choice, and other kinds of the carbon material should be okay. But we don't know. We should to make it and to compare it, and then we'll know the results. But I think that as long as we use the carbon in the material, it should be improve the result. Can you hear me?
Okay, yeah. Okay, everybody is hearing you. You can read the question and answer, please.
This is the 11th question, and the 10th.
Yes.
The 10th is that will the gel precursor reduce the conductivity of the metal oxides? No. We use the polymer. Of the precursor in the gel to produce the gel, and we put the gel in the oven. In the oven, and to heat treatment it, and then the precursor will transfer into the carbon. Transfer into carbon, and the precursor will be formed the metal oxide. So if we use the carbon precursor in the material, and it will be better. It will be used for the conductivity improvement. Is okay? Can you hear?
Yeah, continue, please.
Can you hear?
Hear you? Yes, please.
Please. Okay. The nice is that is there any method to increase the performance of batteries by other than carbon nano? This is the same with the 11th.
Yeah. Okay. I told you choose because I just copy and paste for you, so you choose the questions.
Choice. 他让我try some questions. And which one? The first is that can tin oxide nanoparticles be prepared by Yes, it should be. We used it, but the tin oxide, the size of the tin oxide will be changed quickly. And if we cannot use our designed microstructure, the size of the tin oxide will be grow quickly. So we want to control the size. So we must use the I didn't introduce it detailedly because you can notice that the temperature is lower. It's only 500. It's lower 500, and for the ultrafine size. We use the precipitation process method to prepare it before, but the size of the tin oxide will be grow quickly. So it's not a very if we want to get a very good crystal structure, but when we get the crystal structure, and the size will be bigger. So it's not
okay. So there is we can I send you another question if you can answer, maybe one or two. That's enough, because we need to pass the time for our second speaker. You know, there is another question I just send you now.
Can you send
I sent it now. Yeah, I sent you.
Oh yes, I know. Does the size of the tin oxide nanoparticles before doping present the mechanical property? Mechanical property.
You don't study the mechanical. I don't know. This is just a question. If it can keep the same properties.
Yes, it's not the mechanical property.
You can answer in general and yeah. Please.
You know, for the electrochemistry chemistry property, in fact, actually, we not put our emphasis on the mechanical property.
Okay.
Yes, we just focus on the electrochemical property.
So you can choose now one last question from the all I gave you. Maybe.
Which one?
You choose whatever you like. Anyway, because we don't have time. After we can send the answer to the audience by emails or.
How about
choose any, just the last one.
Last one.
Yeah, one last question we need to answer. Choose any one.
Ah, yes. How about the 6?
Okay.
How to determine the stability of the metal oxides with different voltage? Yes, this question is a very good question, because you know, with different voltages, during the electrochemistry process, the stability of the metal oxides is very important for the performance. So what we have done before is to guarantee the stability of the metal oxides. Yes, it's okay.
Yes, that's fine. So now we would like to thank you again for joining us. We hope that we invite you for another event, and enjoy your holidays. And let's now let me pass to Judith, because she will introduce our next speaker, Professor Khan from Illinois Institute of Technology from United States. Thank you very much, Xiaoxiao.
Thank you, Mohammed.
Thank you
very much.
Thank you, Dr. Xiaoxiao, for the informative session. Thank you, Dr. Baodina, for chairing the session. Next, we move on to the next session by Dr. Ishaque Khan. He is a professor from the Department of Chemistry, Illinois Institute of Technology, Chicago, USA. And his title of presentation for today's webinar is Functional Materials, Potential and Promise. To say a few words about him, he received his PhD degree from Indian Institute of Technology, Kanpur, and did his postdoctoral university at Syracuse University. He has over 90 research publications in peer-reviewed professional journals. He has US patents and monograph chapters. His research interests include nanoscale science and technology, functional materials for applications in catalysis, sensors, energy storage, and biomedical usage. His research work has been highlighted in Science, Science News, and Chemical and Engineering News, and it has been incorporated in premier chemistry textbooks. He pioneered Illinois Tech's professional science program in materials chemistry, the first such graduate degree program to combine modern materials design and synthesis strategies. Over to Dr. Khan.
It seems we cannot hear you again.
Thank you very much.
Okay, very good.
Greetings from the USA and very good early morning from here. First of all, I would like to thank the organizers and the program chairs, Professor Muhammad Bodina and Professor Judith Vijaya, for the invitation to speak at this wonderful conference. I'm very pleased to be here. I would also like to thank a talented group of my graduate students and the postdocs who have worked. Let me take a second. Okay. So once again, I would like to thank a talented group of my graduate students and postdocs who have worked over several years to produce the results which I'm so excited to present here today. My sincere thanks also goes to my collaborators for wonderful collaborations, some of them lasting over a few decades. And last but not the least, I acknowledge the financial support for my work from a large number of institutions and organizations, including those which are listed here on this slide. The title of my talk today is Functional Materials. There are many ways to define materials, but here is one which is highlighted on this slide. That's my favorite one. That is, the materials are the chemical substances that are either being used technically or have potential for such uses. And they are all over around us and everywhere. From the common household water softener to smoke and fire detectors to artificial hips and joints, pacemakers, memory chips, batteries, computer devices, catalytic converters of the cars, photovoltaics for energy purpose, supercapacitors and superconductors. Essentially, they are all the consequence of materials. The advancement in the science of making materials has tremendously impacted and improved the quality of lives that we can recognize. The materials have tremendous impact on the global economy. Remember the catalyst, which is in the catalytic converters of the car. There are many such catalysts. Indeed, catalysts are chemical substances, and they impact the global economy to the tune of $30 trillion, trillion with T, globally. A modern car has over 400 sensors, which are nothing but chemical substances. So you can see the list goes on and on. And chemical sciences, being the science of atoms and molecules, which are the building block of materials, play a key role in the design and development of materials that are needed by the industry and society to solve the modern problems of the current day. Today we live in a world at a time where there are tremendous scientific and technological advancements. At the same time, the society and the humanity is faced with wide range of serious challenges and problems. The problems of unsustainable urban developments, providing affordable health care to the wider cross-section of the society, the staggering energy needs, which is going to be touching about 30 terawatts in a few decades, providing clean water, and not to mention the ongoing pandemic, providing education, safety, security, and food to a larger section of the population around the world. Providing sustainable solutions to some of these problems without compromising our environment, jeopardizing our food supply chain, or contaminating our water remains truly a challenge. Undoubtedly, finding solution to some of these problems will require some calibration and adjustment in our living and, most importantly, consumer patterns to make the planet sustainable for living. Fortunately, there are people, institutions, and organizations who are committed to address such problems. And there are some encouraging emerging solutions on the horizon. Solution to some of these leading problems of environmental, medical, and technological relevance, they hinges on the advancement in making high-performance functional materials. Materials enable technology, which is required for addressing problems and making devices which people use. Therefore, it will not be an exaggeration to say that the overall pace of the development of the industry and society overall is intimately connected to the advancement in making materials, that is, functional materials, to address the problems of the society which we are facing today. While I'm at this point, I wanted to bring it a conceptual point that there is a tremendous amount of fundamental work which goes here. Core scientific knowledge which is produced so that there are applications and innovations and finally making devices with public uses. Now, common public are the general masses who use the devices and the products. They may see the benefit of those products and technology in their lives, but often they do not see the connection between the products which they use and tremendous amount of the fundamental core or basic scientific knowledge and work which goes that leads to the production of the devices which people use. And therefore, it is very important for us, the educators, and I urge this point to my colleagues in academia, to make these connections for them and educate general public that what we do and what they see, there is a great correlations. This is an important conceptual point which I always urge the people who are in academia to make this connection. Now, can the materials which are needed for supporting the technology and making devices be produced overnight on demand? Not necessarily. So the point is this, that how can we make these materials and compounds that are desirable properties and functions to enable those technologies? The question essentially is that how can you produce the structure that produces the property that is required for sustaining the technology and devices? I must emphasize here this point that the property does not grow on a tree. Indeed, it is the structure of the materials which produce property. So as a material scientist or a material chemist, we are essentially talking about the produced materials which are of certain structure, because the structure generates property. This is an important point. So the structure-property relationship lies at the heart of the materials science and materials design and development. And if the academic community realizes this one. So this is an important point. The fundamental task ours is to generate structures or the chemical systems which have specific structures that generate the property. Now, generating such materials with specific or desirable properties, that is the goal of the material scientists. And they cannot be prepared overnight on demand. Therefore, the sustainable effort should continue for making such materials. Now, to demonstrate the structure property relationship, let me take a point here and an example. Example of a platinum compound in which 2 ammonia molecules are bonded to platinum and there are 2 chlorine molecules. So 2 chlorine and 2 ammonia molecules are bonded to a precious platinum metal molecule. In this molecule, this is a platinum complex. When 2 ammonia molecules are bonded to platinum in such a way that the both ammonia are cis to each other, that is adjacent, in an adjacent position, that produces a compound called cisplatin. Cisplatin is the precious anti-tumor drug, which is the life-saving substance, very precious substance. On the other hand, if the two in the same molecule, if the 2 ammonia molecules are trans to each other, that is at the farthest distance, everything remains same. The number of atoms, the type of atom, everything, empirical formula, but only the position has changed. Now, the 2 ammonia molecules are at the farthest distance. This compound is a trans compound, are the same, but this is useless. It's a toxic material indeed. Now, this is a spectacular illustration of that how the structure influences the property. Just the structure, everything remains same. One is a life-saving drug, another is a toxic material. And that tells everything. So it is the structure always which produces property, and we worry about how to produce certain structures. So the continuous and sustained effort is needed to design and discover newer and better materials of right structure to produce desirable properties and functions that are needed for addressing the problems that we are addressing and we are trying to solve. Now, in order to design and develop materials, we have to look into that what are our resources? What do we have to work with? That is our resource is our planet, planet Earth, the planet where we live, the planet where we are born from, the things which it grows, we eat, and what it contains, we use it for our various purposes, including for making materials, get buried into it, and indeed one day will be resurrected from that. So this is the material. This is our planet Earth. Now, in this planet Earth, what is accessible to us is what is lithosphere or the Earth crust. This is the outer mantle of this planet of 70 kilometers deep. This is the outer shell. That is what contains most of the things which you have access to. And we need to look into what is the abundance of various elements into of the known 118 elements. If we look into this one, what is present in this lithosphere, that is in the Earth's crust, 8 elements constitute 99% of it. This is the most abundant elements. First 8, you can see the most abundant ones. Rest 110 elements, they make up only just 1% of the resources. This is an extremely important perspective that this is what we have to work with. And every time when I bring this point to my classroom, to audience, there is always a silence as if they have never thought about and nobody ever told about it. Again, this is the point which I try to get across, and I ask my colleagues in academia to get it across to their students so that to be aware of that what is accessible, what we have to work for. And my research lab and my research effort is very sensitive to this one. I do not encourage people to go and look for a very rare elements to design a substance which could be used in these devices. No matter how effective and smart that device could be, it will be very expensive and only few people can afford it and therefore will have only limited applications. So now that I have illustrated these points, that these are the fundamental things that we should keep as the material scientists in our mind when we go out to design and develop materials that potentially could be of wider application by wider cross-section of the society. Again, this is an important point. In addition to that, again, we have to be very mindful of the clean and green processes, that is, to use the materials for making substances which are non-toxic, don't leave much footprint, and most importantly, use green processes, which entails using less toxic materials, almost no use of organic or corrosive acids, and so on and so forth. Now, once I have laid out these fundamentals, let's look at that what is in terms of the essentials of design and development efforts of materials. These are 4 essential components which are essential and which are basically, they feed into each other. This is a synergistic effect. So they feed into each other. That is essential part of any effort or any serious effort directed towards design and development of materials. One, the design and synthesis of, we are talking about this wet chemistry in the lab. This is very labor intensive. Then the characterization, these materials which are made, produced in the lab are to be characterized that what they are by a large number of physicochemical techniques. These are expensive. And not everybody has got access to all, but world is interconnected. We are very fortunate in Chicagoland that there are national laboratories and a large pool of universities and infrastructure. For example, my students can use Argonne National Lab's Advanced Photon Source. That facility is $250 million worth. Now, not everybody can afford, but this is very fortunate that we have it. Fortunately, there exists collaboration that we can characterize these materials. Not everybody needs that $250 million machine, but we are fortunate. So the point is that this requires large number of physicochemical techniques to characterize. Then materials evaluation, what kind of properties they have, what could potentially they will be used. And in all these computational methods, simulations and modeling play a very important role. So I realize all these things that these are so important for any serious effort of materials design and development. So while I was launching my research program at Illinois Tech over 2 decades ago, I realized that there has to be a serious teaching effort so that the students can be taught all these tools and techniques and they become productive members in the group or in the workplace. So not only that I launched my research program in materials design and development at Illinois Tech, but also I launched a formal teaching program, a new graduate degree program, which is essentially dedicated to materials design and development, along with all that which requires or which goes with this one. So that is, let me talk to you briefly in a minute, what is that teaching program before I return to my research effort. So this is called Materials Teaching Programs at Illinois Tech, which I developed actually over 2 decades ago about. It's a professional science, a formal master's degree program in materials chemistry. This program combines the modern materials design and synthesis strategies with innovative materials characterization techniques, including computational methods, modeling, simulation, and interdisciplinary skills which are needed in business, which is, for example, project management, legal, ethical, and regulatory aspects, environmental regulation, risk assessment, intellectual property, and communications and leadership building skills. These are very non-conventional things. When I designed the program, this was very novel. And so this was something very unique. This is an innovative approach, essentially, in higher education to prepare. This is to give a new degree to prepare graduates for science careers in business, government, academic, and non-profit sectors that combines rigorous study of material science with business principles. This multimedia-based program, which is viewed as a model, offered currently throughout US and Canada. And there is a talk because of the intense demand that to open this program globally. This fills a gap in the higher education curriculum. And there was nothing like this available when we launched this program. More details are available, of course, at our department website for the interested audience. So this is an education effort in the materials design and development. Let's turn to my research program at Illinois Tech. Now, we are particularly focused on the design and development of materials composed of transition metal oxide clusters known as polyoxometalates. We use these materials to make inorganic materials. Organic and organic hybrids are composite materials composed of bonds, coordination polymers, and metal organic frameworks. And then these materials find applications in many fields, including in heterogeneous catalysis. For example, in DNOx, I will tell you in a moment what DNOx is, oxidative dehydrogenation. That is the functionalization of the vast reserves of hydrocarbons which we have, which are currently inert, to make them valuable industrial feedstock chemicals. Materials for sensors, especially for gas sensing and nitrogen oxide sensing, that's NOx. NOx is nitrogen oxides. For the energy storage, gas separation, and biomedical uses. Today's talk will be on functional materials with applications in the DNOx catalysis, that is removal of NOx gases and sensing up. So this talk revolves around a diatomic molecule called NO, or nitric oxide. Now, nitric oxide is one of the smallest molecules and of tremendous importance. It has application in biomedical uses because a small amount of nitric oxide is produced in the body, and it is required for supporting life as a neurotransmitter and muscle relaxant. At higher concentration, nitrogen oxide becomes toxic materials, and nitrogen oxide is produced by automobile industry, industrial establishment, and sometimes, and of course, it is generated during the thunderstorms. So today we'll be talking about this nitric oxide. This has got at elevated temperature, at elevated concentration, it is a toxic material. Therefore, we need sensors to sense, to detect, analyze, and monitor its concentration. And at higher concentration, we need technologies to remove it. So the technology for removing is catalytic technology, which is called DNOx. And the technology for sensing, it is called NOx sensing. So there are three dimensions to this problem. Biomedical applications, that is, it is required in a small. So you need materials which can deliver a controlled amount of nitric oxide in the physiological conditions in biological systems. Such materials are called nitromedicines. And then you need technology to monitor these. These are nitrogen oxide sensing. And you need technology to remove catalytically excess nitric oxides wherever they are found because they are toxic. So these are three-dimensional problems, and my research group has been interested in all of them. But of course, I cannot cover all of these things. I will try to illustrate with the help of examples of the materials developed in my group, functional materials, for the DNOx catalysis, the catalytic removal of NOx gases, and the DNOx sensors, or the NOx sensors, the materials which are used are developed in my group for making NOx sensors. So let me tell you that where NOx comes. The most of the polluting NOx gases, they come from automobile industries, about half of them. 27% from utilities. There are heavy industries, industrial establishment, and rest from the commercial sources. Now, nitrogen oxide, which is a combined name of NO and NO2, nitric oxide and nitrogen dioxide, these gases are environmentally detrimental over a certain concentration. Interestingly, as a small amount, it is a life-saving thing, and at higher concentration, it becomes toxic. And therefore, prolonged exposure of nitrogen oxide above 0.5 ppm level is toxic, and therefore there is a need to both sense or detect and remove nitrogen oxide gases from the industrial exhaust. So this sensing and DNOx, that is removal of, which is catalytic process, is of contemporary interest. It is because of the increased environmental protection concerns, stricter government regulations for the detection and removal of hazardous chemicals from the emissions, nitrogen oxides, carbon monoxide, sulfur oxides, so on and so forth. The USA EPA has been tracking major pollutants. Of these, most of them have decreased since the clean air of 1970, except NOx. The pollution of NOx has increased by 10%. And therefore, there is an urgency in finding, there is a need for efficient sensors to monitor nitrogen oxides and remove them catalytically, which is the DNOx process. But let me tell you that detecting NOx is NOx sensing, and removal of NOx is DNOx. NOx gas sensors are generally, which are the state of order metal oxides, Typically, they are made up of tin and tungsten oxides. They operate at higher temperatures. They require continuous supply of energy, and which is not a very good thing. So this is an energy issue as well. The desirable properties of NOx sensors are the sensitivity, selectivity, stability, reversibility, reproducibility, short response and recovery times, low cost, and of course the small size. These are very idealistic and desirable features. What are the typical problems plaguing this NOx sensor industry? Drift, inadequate selectivity, inadequate sensitivity, degradation of sensitivity over a period of time. What is needed? We need, this is my way of saying the problem, we need a new breed of efficient or functional sensor materials required to improve the sensitivity and selectivity. And therefore, the search for the new sensor materials continues. And that is one of the foci of my research work. The other dimension of this problem is removal of NOx catalytically. The current state of art or technology, this is called DNOx, and this uses vanadium and vanadium oxide and tungsten oxide supported catalyst on a porous titanium oxide anatase phase. The conventional process of DNOx, which is SCR, on a good day it removes 65 to 80% of NOx gases. Rest still goes into the environment, which is not acceptable. Moreover, it uses ammonia as a reducing agent. Ammonia itself is a pollutant, and slip of ammonia occurs, which is also a big no. So what can be done? This is out of box thinking process that nitrogen oxide, which is made up of nitrogen and oxygen, both are benign gases, both are present in the air. If they could be catalytically decomposed into their components, and this is thermodynamically feasible. You can see delta H is negative. However, the reaction rate of this decomposition is very slow. This reaction is almost dead. But if this could be made feasible, then of course that will be a wonderful thing, because the products are environmentally benign substance, namely oxygen and nitrogen. So when such problems occur, we know that we should turn to catalysis, that we look for that if there is a catalyst, then catalyze this rate of this reaction, increase the rate of, to make it commercially viable. When we talk about catalysts, we talk about zeolites, or just zeolites are the outstanding catalysts, as we know. So it turns out that ZSM5 is this one aluminosilicate. These are three-dimensional materials. ZSM5 alone does not do anything. But when transition metal oxides are loaded on the aluminosilicate zeolites, then act as a catalyst and significantly enhances the rate of reaction. However, the reaction rate is still not large enough to make this process commercially viable. At this point, essentially, this calls into attention too. But there is a hope that what is the role of zeolite and what is the role of transition metal that catalyzes this reaction. So this is a typical zeolite, ZSM5, which has got three-dimensional channels and pore. Now these pores, and there is not much time to go into details, but suffice to say that they have got well-defined channels. Because of this, they exhibit what is known as shape selectivity. So here is an example that out of three products which could be formed in this reaction, it selectively generates only the rod-shaped molecules because of the strict size. All other these intermediates, they are stuck in this cavity. They cannot get out. This is called shape selectivity. And the zeolites are outstanding shape selective catalysts. So that is an important thing to realize here. And remember this point. On the other hand, metal are used in a large number of heterogeneous catalysis process. Okay, they are used in many processes, but my focus is here on the catalysis and chemical sensing. Transition metals, they are outstanding redox catalysts. That is, they can undergo oxidation reduction reactions. They can accept electron. They can give electron. This is called redox process. This redox process lies at the heart of the catalytic processes which they catalyze. And there are a large number of industrial processes of economic consequences are catalyzed by transition metals. So remember this point, that when you use zeolite as a catalyst, they exhibit shape selectivity, but they do not exhibit redox chemistry. When you use transition metal, then shape selectivity is to be compromised and only the redox chemistry is to be retained. So again, when you use zeolite, the shape selectivity is observed and redox chemistry has to be sacrificed. When you use transition metal, then redox chemistry is there, but shape selectivity is lost. Now the point is that, and this is the point I articulated some time ago, a decade ago or, that is it not possible to make a new breed of materials where the shape selectivity of zeolites is married with the redox chemistry of transition metals. So a new breed of material where we can have both worlds. And that was the challenge, how to make those materials. To cut the long story short, we employed a class of materials called transition metal oxides. Because if you want to have redox chemistry, you have to have transition metals. Aluminosilicates or zeolites do not have transition metal, therefore they cannot have redox chemistry. So we started talking about transition metal oxide clusters. This is a large number of material, growing large pool of material. This has been known for a long time. There's nothing new about it. But they have been sitting there. Not much was done in terms of the materials design and development by using them. So we said, and these are various kind of transition metal oxide clusters. Thousands of them are known. Even quite a few dozens of them have been made in my group itself. So these are important structural types. They are incredible building blocks for making various kinds of materials of different shape and structure. So we said that we need to use them as building blocks to make a new class of zeolite type material, which we call zeolitic materials. And let's see that if they can do this task of catalysis better than known materials. So this begins the journey for the design and development of a new class of zeolitic materials composed of transition metals. Now, it turns out that these transition metal oxide clusters or PAM, polyoxometalase, could be made very relatively easily. This chemistry is the chemistry of first row transition elements, group 5th and 6th metals, dirt cheap. This chemistry could be done in water. Oxygen is the ligand. You cannot ask anything better than that one. This is inexpensive, dirt cheap, environmentally benign, with the least effort and the least expensive materials. And you can do first class chemistry, just the simple building blocks. Some of these metal oxide clusters are larger than small protein. You can see it's in nanometer size. So they are sitting nano building blocks, could be made in 90% yield or over. Once you make, they are rock solid. They don't go anywhere. They're stable. And this is what you need for doing all kinds of things which you want in the real world. So here is the philosophy for making such materials. Transition metal oxide cluster, we said that we should have to, and there are large number of them are available. So you can pick and choose. This is our building block. We need to have linkers which can connect. So this is basically this is classical thought process, that how you visualize that this is a target unit. So we need the linker. This linker could be inorganic or organic. There are large number of ligands. So you have got large number of permutation and combination. This is metal oxide cluster. There are large numbers, linkers, infinite number of linkers of organic, inorganic ligands are known. Conceptually, you can make this building block. Then it opens the door for virtually limitless class and types of materials. And the technology of making we use generally hydrothermal synthesis and Teflon pouch. So you can see here, we generally don't use the conventional glassware which requires acid and large number of organic salts. This is very simple. Teflon pouch, here you can see, you can have hundreds of, at least dozens of Teflon pouch in one reactor, and you can see only few drops of the solvent. Generally it is water. And again, this is the first row transition elements, dirt cheap, environmentally benign. This chemistry could be done hydrothermally, and generally it yields 60 to 70 to 90% of the compounds in crystalline form, which could be characterized. So I want to take you on the journey of this. This is, for example, one cluster, which essentially it is made up of 18 vanadium, 42 oxygen, the red are oxygen, green are vanadium. This is like a soccer ball with a hollow. At the center of this one, you can fill this belly with a large number of these type of molecules. As you change these guest molecules, the electronic structure and magnetic properties of this soccer ball shell changes. And this is 18 plus 42, 60. Remember the buckyball, but this is not carbon, this is metal oxide. Very symmetrical molecules. Many of them are known, some of them are made by us. Now the key was to activate these surface oxygens. You see this at 18 antenna type of oxygen out, sticking out, terminal oxygens. That was, we activated them, and that was the trick. This requires a little time for us to learn that one, but that was actually the tipping point. So we can make materials now by using this technology, by using them as a building block, using this as a, we wanted to introduce different linkers. So we chose this as I call the Lego, so for making toy. So this is the Lego, and then we use these linkers to generate, this is the one-dimensional nano wire type of material. You can see the building blocks are intact. They are linked with linkers in one-dimensional way. Now we can change the linker and generate two-dimensional nano sheet type of materials. And finally, a three-dimensional zeolitic materials. This was the dream. This is the three. If you take a slice of this three-dimensional material, so far I have shown you one-dimensional, two-dimensional, and finally three-dimensional. This was the climax. If you take a slice of this material, you are looking at this. So these are the building blocks connected through these linkers. And this material has got three-dimensional channels. So you are having this rectangular box, and you are looking into well-defined cavities and channels which are found in conventional zeolites. Here, we can change these building blocks, these clusters. We can change these linkers. In this case, these are active transition metals. So you are looking into a tunnel structure whose boxes or cavities are defined by polyoxometalate or transition metal oxide clusters. The walls of these tunnels are embedded with these active transition metals, which are reactive catalytic sites. And because of our building block approach, we are making them from the bottom up approach. Therefore, we can change these Legos and we can change these active sites. This is something non-trivial. This has not been accomplished of this level that we can design now our zeolitic. This is a new breed of three-dimensional zeolitic materials made up of transition metal clusters and transition metal active sites, whose sites and clusters we can change. And the size of this box we can change by changing these linkers. This kind of control on the on the structure of materials, this is truly functional materials whose functions and properties and structures we can fine-tune at the atomic and molecular level. Such kind of control has not been known earlier. And we were the first, essentially, to make this kind of materials from transition metal oxide clusters. And of course, after we made it, this was published into the top journal of the field, Angewandte Chemie. And of course, after that, we made several dozens of that one, and we are very interested. And of course, a large group of people now worldwide joined, and this effort has been going on at a brisk pace. Now, I want to take another example of this. Remember that this is the launching of a new breed of materials, a new class of materials. You can have you can just change this one functional groups, and I don't have time to go into, I'll take just two examples. Here is the vanadium oxide, VO5. You can decorate with phosphate. So this is a new building block which is generated in situ. And such simple building block generates one of the most complicated structure known in inorganic field. This donut type of structures, again, they have got well-defined channels and cavities, similar to zeolites. And the simplified version of these materials are like this. So you are having three-dimensional tunnels. Where the tunnels intersect, it generates cavities. These cavities are the one which are molecular reactors. That is where shape and size selectivity comes into being. These structures are very open and do lots of neat things. To move on this one, another example, and this is the class of materials, again, all developed here. So this is This is an example of what we say sometimes as naked palm, that is simply transition metal oxides. So these are made up of, these are 6 octahedra of vanadium, and the center is an iron. This cavity could be filled with iron or any of the first row transition elements, even the main group elements. So there is a possibility you can change this one. Now you can bring organic molecule around it and rock it up. Replace these oxygens with alkoxy groups of triethanolamine, for example. So you can convert this purely rock type structures into a soft materials by wrapping this core, this hard core, into a soft chicken fat, which I call. Okay, so this is a soft material which is grafted with organic. 2 arms of this triethanolamine are engaged with the ring of the metal oxide, and third is pendant. This gives the possibility to anchor. Now this material becomes soluble in physiological pH, in the biological conditions, and you can basically inject it into the body. This is very benign materials, and this gives the possibility to anchor with the enzymes and biomolecules. So this is a very important class of this thing. Now remember one thing important, that in this process of functionalizing, as it is called, this gets reduced. And reduction means these are the blue ones are the vanadium centers, red are oxygens, and rest is organic. Then this reduce has got 1 unpaired electron. So there are 6 unpaired electrons, and they interact in a nice way, that this is a ferromagnetic. So this is a single molecular magnet. Again, a big deal, making single molecular. We can fill this cavity with a number of various metals, and therefore we can fine-tune the magnetic properties of such materials. Not a trivial job. Single molecular magnets are very important. You can make, you are lucky. But altering systematically magnetic properties, that is a feat. And indeed, we were able to do that, but fortunately. So this have now an extensive chemistry, a good magnetochemistry, ferromagnetic systems, and all kind of nice things. I want to show you. I don't have time to show. This is the magnetic property that shows that there is a strong ferromagnetic coupling going on within the clusters. 6 of these centers, they interact, and they interact with the center molecule, this atom, whatever it is. And you can change this one center. By changing the central cavity metal, you can alter or systematically change the magnetic properties of the molecule. And we prepared a series of this. I just want to bring your attention to this. This is called magnetic moment, which is related to the unpaired electron or magnetic properties. In manganese 2 system, when the central cavity is manganese, when this is manganese, it has got 5 unpaired electrons coupled with 6. So magnetic moment is 8.8. In the periodic table, you go from left to right. After manganese is iron. So you are systematically increasing number of electrons, and hence decreasing the magnetic properties or pairing the electrons. And therefore, you expect a systematic decrease in the magnetic moment. You see this one. After manganese, 5 unpaired, then 4 unpaired. This is decrease. Then 3 unpaired, 2 unpaired. And this is systematically. This is a textbook. This is a textbook example of the series of molecular magnets where you can fine-tune the magnetic properties. In the previous example, I showed you can fine-tune the redox properties and the cavities, again at the molecular level. Here, you can fine-tune the magnetic properties of single molecular magnets at this molecular level. Again, something unprecedented, very hard thing to do, but this is possible by the approach which we have developed. So these molecules, as they cluster, the single crystals, they pack like this, as if they are begging to shake hand. You can see these arms, pendant arms of triethanolamine molecules. So we said that why? Well, let us give them this opportunity to embrace each other. So we put some glue over here, glue in the form of the ligand, and then immediately it forms actually. So here with this is the single molecules. We put this tricarboxylic acid, benzene tricarboxylic as a glue, and immediately they came together. So they formed this tetramers by this glue by covalent bond. And this is the atomic force microscopic view of this nanostructured material. Each bright spot here is one tetramer. You see, this is tetramer of this material. This is functionalized materials of building block for making this nanostructured material. Each one is about 5.5 nanometer dimension, and they're forming nice hexagonal lattices, and each bright spot is separated with other by 12 nanometers. So indeed, this tells the potential of new materials. And these are, remember, these are magnetic materials. So you are talking about a new class of magnetic materials where the individual magnetic centers are isolated from it. They are monodisperse. And there are lots of potential applications in terms of potential molecular imaging, contrast, and memory devices. This is something, it's a very fascinating thing, and I can spend a whole 1 hour talking about, but we don't have time. Furthermore, these same materials could be used for making new class of colloids, which I don't have time to talk much about. This is a new class of colloids never observed before. You can see this one, and of course there are technology involved that how to make it. Not only that, they produce some coil type of structures which are unprecedented, and we are still looking into this one. Again, there's a lot of chemistry. This is one PhD thesis of my latest student, Dr. Swenson. So this opens this tremendous doors for a new class of functionalized materials. So far we have shown you two classes of zeolitic materials, one class of organofunctionalized magnetic materials, which can be used for magnetic devices, molecular imaging substances, and colloids. Now I want to say there are a lot more stories into it, but I want to stop here and show you some applications, especially which I promise you for the DNOx catalysis and NOx sensing. So this is a work of a PhD thesis, which is summarized on 2 slides. So of course, these are the conditions for testing DNOx catalytic activities. Of course, the goal is to remove nitric oxide. The reducing agent, we are not using ammonia, rather we are using a hydrocarbon, which is environmentally benign, propylene. And these are the conditions that in the presence of oxygen, without oxygen, of course, the real working condition is presence of oxygen. These are the preparation of the catalyst. This is one of those zeolitic materials, which I showed you earlier, vanadium oxide V18-based systems. This is the preparation method. What it does, this is what important. This is the kind of, this is the catalyst. This is a new class of nitric oxide. You see, after certain temperature, this removes 100% nitric oxides, qualitative. The conventional catalyst, the state of the art, it removes only 65 to 80. This is 100% at a certain. And this catalyst is quite stable. What it makes, of course, how does it do that one? It essentially converts nitric oxide into N2. You can see this one. So NO goes into N2, which is a dream. Am I claiming that we have solved this problem? Well, this is a huge thing. Of course, there are many issues to be solved, but this is extremely promising. And this property you see because of the new class of materials of improved structure and improved property, and hence improved functionality. What you want to see that all the nitrogen, all the NO is going into nitrogen. This is you can see, which is what is the desire. And the carbon is going into carbon dioxide, not carbon monoxide. If it goes into carbon monoxide, it is a big no. You see the bottom plot, this is carbon monoxide. So it is all carbon is going to carbon dioxide, which is very desirable. Of course, carbon dioxide is a greenhouse gas, you will say, but carbon monoxide is poison. So this is the best you can do in this condition, that everything into N2 and CO. That was about the DNOx catalysis. The new materials are very promising in that one. And again, that was the work of a PhD thesis. The next is about the sensor properties by using same materials. Here there are some technology involved in devising sensors. And we did not know how to make these sensors much, but essentially we had to learn and make these sensor devices made up of rubber. So this is the final sensor chip, which is having a coat of our new materials on it. Now we put it inside a sensor testing system where there is a flow of nitrogen oxides with other gases, where you can control the temperature, where you can control the humidity, where you control the mix of gases to simulate the working condition where nitrogen oxide sensors are needed. Remember that all the nitrogen oxide sensors known so far are high temperature sensors with very little possibility to change in their working situations or improve their selectivity, are very limited. But listen what we get. So here different kind of sensors made up of either zinc or cadmium or different kind of things. So generally you will see that we have tested a range of concentration of nitric oxide, starting from 5 ppm to 250 ppm. Of course, you can go down further. And what you see that we are measuring the resistance of those sensor devices under sensor condition, under the exposure of nitrogen oxide at different temperatures. Now you can see this is a room temperature measurement. You can see that in the presence of nitrogen oxide, the sensor response, the resistance increases. When you turn off nitrogen oxide, sensor comes back. This is called reversibility. This is called response reversibility. This reversibility you can see from 5 ppm to 250 ppm. This is perfect, 100%. Now in the sensor world, this is almost unknown. If you get only 70 to 60% reversibility, you are lucky. But here you can see the quantitative. This is almost just perfect reversibility. The response time, it is less than a minute, and perfect reversibility. And the response of the sensors, it covers the entire range. So this is a new class of sensor materials, and they operate at room temperature. Yes, at room temperature. Most of the other sensors operate at 200 to 400 continuous need of energy. Here, there's zero energy. So this is a tremendous, again, the functionality of the material. So our sensor materials, they respond, they are room temperature NOx sensors with good sensitivity, rapid response and recovery time, long-term stability, and complete reversibility and reproducibility. This is something unheard of these ones. One problem you worry that cross sensitivity, whether the sensor is selectively taking nitrogen oxides or others. So you can see that this is very selective to nitrogen oxides and not selective to others which are also present under the active condition, the real world condition, they are also present in the mixture. So you can see, and the sensor operates at various, but it operates best at room temperature, and at higher temperature, there's no need for to operate at higher. But again, the selectivity and sensitivity remains, and the cross sensitivity is very selective for this. Now, one thing which you worry in the sensor world is the humidity, because there is always humidity, and humidity kills sensor. No matter how wonderful sensor, if you expose it to humid condition, humidity will kill the sensor response. Now you can see we have tested these sensors from 5% relative humidity to 85%. This is almost water. So you cannot have any more humidity than this. And in all conditions, the sensor is stable for long period of time. And this shows all that different relative humidities, the response and recovery time, this is all perfect. So this is, in a sense, you can see that this is a new breed of sensor materials. Again, because we have generated a new class of materials where shape selectivity of zeolites is combined with redox chemistry of transition metals, and their properties could be altered at the molecular level, at the atomic and molecular level. So this atomic and molecular control, this is the key, and which is hard to achieve. But because of our approach of designing functional materials, it is possible. And no wonder it shows such promising results. Again, there are many other results, but today I have tried to cover only the talk of functional materials in applications towards nitric oxide, both in the biological world as well as in the sensor and the DNOx catalysis world. So what I have shown to you, that we have succeeded in designing and developing a new class of functional materials which are composed of well-defined building blocks. And they are crystalline materials, defect-free structures, whose structures are determined by X-ray crystallography at atomic resolutions. Exactly know what the structure is, how it looks like, and we can change that also at our will and wish because of the technology of making them, which we have developed by using bottom-up molecular building block approach. So these are monodisperse reactive sites with reactive sites like manganese and other things decorated or incorporated into framework which we can alter. So this is atomistic changing, which is very hard to achieve, but we can do that. They have pores, and the pore properties could be changed. The channels and cavities, which are filled with exchangeable counter ions, which can exchange. They are potential DNOx catalysts. They are a new breed of promising NOx gas sensing materials. So we have generated a new generation potential gas sensors and molecular magnets, which have potential applications in biomedical imaging. So with that, I think I will stop here. I hope that I have been able to give you a flavor of the functional materials, not only their development in the research lab, but also the effort for launching degree programs to teach such kind of efforts, which are only in the primary literatures. So I will stop here and would like to give you thank in many languages. First, shukriya. Second, dhanyavad. Third, thank you. And read your own language on the slides. Thank you very much for your attention. I'm glad that you are able to join me today. Thank you.
Video. Thank you, Dr. Khan, for the wonderful lecture. We have few questions here from the participants. First question, can we produce reusable mobile batteries to avoid electronic waste?
So you see that the batteries is not my field, but I'm very familiar with that. So reusable batteries is the dream. And again, this is a material thing. And I'm convinced, and indeed, only so much I can do in a research group. But there are many, every time I go to conferences, my friends who are in the battery world, they basically try to convince me to change my field to go to battery to design these materials. So indeed, it is possible. It is absolutely. Remember that the building block, now what I have shown you, this is the ultimate control you have got on atoms and molecules by this approach. So this way you can indeed design materials. And this is potentially possible that there will be future. And as a matter of fact, as you know, that the battery was the subject of Nobel Prize in chemistry last year. And that was a research project which I assigned to my graduate and undergraduate students, and they were poster presentations. So this is a wonderful thing. And I think that time is ripe, that yes, it is doable potentially, in my view.
Thank you. Next question, if structure generates property, some fungi shows high resistance towards extreme heat like sun heat. Why don't we identify the material in it for resistance and explore its property?
Could you please repeat the question? I missed something.
If structure generates the property, some fungi shows high resistance towards extreme heat like sun. Why don't we identify the material in it for resistance and explore the property?
Fantastic. Great question. Great question. So you see that this is something, this is what I love, that these at the heart of many things which are going on in the biological world, there is a metal system. And that we have to understand. Like the synthetic oxygen, the carrier of oxygen is a hemoglobin. The theater place is a complex molecule, which is basically a coordination complex of iron with porphyrin. And that is where oxygen goes and binds. So we need to go into this biological system and develop, again, a molecular level understanding of what is going on at this central place. Once we understand that is the structure, we have to determine its structure in the in situ condition, the real world condition. And now this technology is becoming available that you can do in the real time. For example, I mean, can you believe that one of my colleagues put one of the insect in the advanced photon source X-ray beam, and the real world was able to determine the structure of the muscle. And this is how you understand that how muscle fail to work. So we have to go at that. And such kind of technology and instrumentation is becoming available. So yes, we need to develop understanding. And one day, once we develop that thing, we'll be able to at least understand that what is going on. Whether it will be possible to change, whether it will be good to change that one, something I worry about, that we should not tamper with what is going on, because the nature, or I should say God, what he makes these things, those are the best. We'll never be able to become smarter than that, but we should be able to develop that materials, and we should be very careful not to tamper with that one, because the natural system is the best at the work. I know, as a material scientist, I know the more I understand, the more I believe in nature, that what a super system we have got. But we should at least be able to appreciate and perhaps and let me say that perhaps we can be more grateful than for what we have.
Yes, true, sir. Next question. How will you optimize the amount of the catalyst usage? And are you using high temperature to produce these materials?
Oh, these materials are produced at such a benign temperature, usually less than 150 degree. And they are produced in water. We don't use acid. We don't use organic solvents. Actually, it is almost forbidden in my lab. My student cannot, because I'm very sensitive for the environment, very sensitive. And I teach and train the group of people that I lecture in my lectures, and I never tired saying this thing, that you have to be very careful about the planet. You have to be very careful about the environment. So we very low temperature operation, very low. Water is our solvent, low temperature with the minimum energy, and oxygen is our ligand. And first row transition metal, all benign, iron, manganese, which are found in the biological system. That is what. So we are very sensitive about the abundance, which I show you in the earth. Because if somebody comes to me that, hey, I have got a wonderful things made of technetium or rhenium, I said, get out of my office. Where do you get these things? Where are you going to buy these things, right? Even if you can, smartest material, that could be used only by 3 people in the world. I'm not interested in any problem, in solving such problems of rich people.
The last question. How much reaction rate is increased by using copper ZSM5 in decomposition of NO?
You see that this is what is the key. That is what triggered me. That is what get me going on this problem. So this was something, that is what I started thinking, that what is the role of metal and what are, if you use only metal, there is no reaction, no catalysis. If you use only zeolites, there is no reaction. So when you marry them, you marry the zeolite with transition metal, then the activity comes. So actually it is the redox property of the transition metal that is responsible for catalysis. But since it is only doped into the system, it is not operating at its best. Then I went on and produced a material where everything is neatly tied. Now every transition metal is exposed fully. So you can take advantage of every metal, every metal. So this is monodisperse catalytic materials, which are resolved at the atomic level, and you can change it. So that is what the catalysis is, because of the transition metals. Now, once you fully expose it, you get the best out of them. And since they are embedded in the wall, they don't go anywhere. They don't go anywhere. The doped materials have the problem that they segregate, and over a period of time, their performance decreases. And most of the catalysts today, which are used in the industrial world, suffer from this problem because they are not designed atomistically from the bottom of approach. So some of them are wonderful catalysts, but they degrade. And if you want to change properties, no way, you cannot do that. But from the approach which we are, you can see, I mean, again, today there was less time, but you can see that this is just one set of material. You can just design any material from this approach. So this is the field is just open, wide open, and there are a huge crowd have jumped in. So I'm glad that, this problem is good for me, that I rather prefer that people care about what I do rather than don't care and nobody joins.
Yes, Dr. Khan. Thank you for the informative session. There are so many questions. Again, it is coming in the chat box of the YouTube. Because of want of time, I have given your email ID to our participants so that they can ask their questions to you directly in email.
Oh, so you have given me some homework.
Yes. After the webinar also, this relationship should continue in research.
All right. Thank you very much for the opportunity. I'm very excited and glad to talk to this wonderful group of audience.
Yes. And for your kind information, totally we have 1,770 registered participants from almost all the states of India. I have just counted 22 states in India, from Jammu Kashmir till Kanyakumari, and 17 countries: USA, Ukraine, Iraq, Morocco, Russia, Algeria, Nigeria, Canada, Kuwait, Chicago, China, Maldives, Egypt, Bahrain, Saudi Arabia, Ethiopia, Africa, South Korea. It goes on like that. So since you asked me, I just wanted to express the registered participants from various countries also. So it's very glad to hear you, Dr. Khan. And there are few announcements for the participants. Regarding the feedback link, kindly fill both the links for day 1 and day 2 today from 5 p.m. to 9 p.m. It will be enabled only from 5 p.m. After that, you will get a link for your e-certificate. Kindly fill your details correctly. If you type your details wrongly, you cannot get new certificate. I request you to kindly fill the details in the link correctly, and per day we will send only 200 certificates. Kindly be patient and you will receive your e-certificate before 30th June 2020 surely. Please don't fill my inbox like you did yesterday about the feedback link. Please wait till 30th June 2020. You will surely get your e-certificate. If you don't receive your e-certificate till 30th June, then you can please mail me, and till that I request you to be patient. I request you again not to send many emails to me regarding the feedback form. It will be open only from 5 p.m. onwards. Thank you. And now it's my duty to propose the vote of thanks. There are so many persons behind the program who made this program as a great successful one. The roots of all goodness lies in the soil of appreciation and thanksgiving. First, let me thank the Lord Almighty who gave me the strength to organize during this lockdown period and for his abundance blessings. I thank the Loyola College management, Rev.Dr. Francis P. Xavier SJ, Rector, Rev.Dr. Selvanayakam SJ, Secretary, Rev.Dr. Thomas Amritam SJ, Principal of Loyola College, for their support and motivation. I express my sincere gratitude to Dr. M. Bavodina, Professor from University of Bahrain, my co-chair in the webinar, without whom I could not have planned so meticulously. I sincerely thank all the 4 speakers of today's session, Dr. Stefano, Italy, Dr. Rabba from France, Dr. Xiaoxiao from China, and Dr. Khan from USA, for their generosity to accept to deliver the lecture. I honestly thank the Loyola College technical team headed by Father Justin Prabhu SJ, Director, Office of Media Relations, Professor Samson from Viscom Department, Dr. Xavier Raj, 3LIC, and Mr. Sudhagar for the continuous support, and only because of them, we could visualize these 2 days webinar without any interruption. I am also thankful to Professor Samuel Johnson and Mr. Sohail of VIT Andhra for their suggestions and motivation. I wholeheartedly thank Dr. L. John Kennedy from VIT Chennai, Mr. Gerald Fermi and Ms. Jasmina Sanctus for their moral support and constant encouragement. I also thank Professor Simeon from MCC for his support. Finally, I wish to place my gratitude to each and every one of the participants for their enthusiasm and active participation. Thank you one and all. See you soon in some other research platform. Thank you again.
Bye-bye.
Bye.